Let's talk about degrees and radians. We've got a circle here. The radius of the circle is 1. Now we've got an intuition whenever it comes to the idea of angle. So if I was to draw a line from the origin here to a point on the circumference of this circle, it would create an angle with the x-axis. Now we're used to thinking about this angle in terms of degrees. So what we do is we split the circle into 360 little segments, and we say that each one of those is 1 degree. This choice of degrees is really an historical thing. There's no reason why we can't split the circle into a different value. So for example, well, my name is Ross. If I wanted to, I could split this into this, what would be determined by in the degrees is 90 degrees, but I could call that, if I wanted to, just 1 Ross, and I could call the angle from here all the way around to there as 2 Rosses, and all the way around to the 270 degrees I could call that 3 Rosses, and all the way around to a circle I could call 4 Rosses. So in order to ground the circle you go around 4 Rosses, and I can get any other angle in between. So I can get this angle up here, which would be a half a Ross, okay, or I could get a quarter of a Ross, so on and so forth. So the choice of this 360 degrees is really just arbitrary, and we can choose whichever value that we would like. And there's a particular reason for choosing one particular value for this scale of this angle, and that's what we're going to talk about whenever we talk about radians. So I have the same circle here, and I've split it into the 360 degrees, so you can see the degrees here, and this angle here, and we see at the moment is 23 degrees, and we can adjust that 1 degree at a time. So if we zoom into this and have a closer look, you'll see that we can adjust the angle here in single degrees at a time here. Now what we said was we wanted to try and find a way of equating angle with the idea of length, and we said that what we want to do then is equate this angle. So take this arbitrary angle here, say 17 degrees, we want to be able to equate this 17 degrees with the length of this arc. So we know how to do that because we know that the circumference of a circle is going to equal 2 pi r, and we've wrote that down here. Circumference of a circle is 2 pi r. Now if we're assuming the value of r for the moment is a value of 1, then we can say the circumference is 2 pi. So don't get lost in this. All it's telling you is that if you draw a circle out of radius 1 and then you measure all the way round about the circle, you'll get a distance which is 2 pi. Well, pi is 3.14, so you get a distance there of 6.28. So now I've added in the actual arc lengths here respective to the value of degrees. So for example here, this degree 17 degrees, then the arc length here is going to be 0.29670 and so on. So we can adjust the values here over degrees, and you can see that the arc length increases. So if this is correct, whenever I go all the way around about a circle, then if the radius is 1, then the arc length should be 6.28, which is 2 pi. So that's what we get here. So let's have a look and we'll see what the arc length is for an angle of just 1 degree. So we've moved this round so it's just 1 degree here, and we can say that 1 degree, then the arc length here is going to be 0.01745. So if we wanted to work out the arc length whenever we're working in degrees, then we know that the circumference is going to be 2 pi and r is a value of 1, so we could just say the circumference is 2 pi. So therefore the arc length is just going to be a fraction of the full circumference. So in this case here we're splitting it into 360th of parts. So the arc length then is going to be split into 2 pi divided by 360. Or equivalently, you could say that's the same as pi upon 180. We're just cancelling out the 2 with the 160. So here we've got a method of equating angle with length. So we can say that if we had an angle of 1, then the length is going to be pi divided by 180. So if the angle was, say, for example 2, then we would have 2 times pi upon 180. If the angle was 5, then it would be 5 times pi upon 180. If the angle was just a value n, then it would be n pi upon 180. So in order to change from angle to length, what we do is we multiply by pi, divide by 180. So this is a way of equating angle and length. We multiply by pi and we divide by 180. But as has already been stated, this scale here for the angle, choosing the 1/360th, is very arbitrary. We can choose whatever scale we want for our angle. Now there is one particular scale that makes things a lot simpler. Now I've drawn this red line in here. Okay, so what we'll do is we'll move the angle all the way round to this red line and we'll see where it gets to. Now it's not going to sit exactly on top of it, but it's going to be close. So we can say here it's approximately 57 degrees. Now what's special about this particular value for our angle? Well, we can see here that the arc length is approximately equal to 1. So that means that if we were to zoom in a bit, we can see that this arc length here is approximately equal to 1. So that is, this length here is approximately equal to this radius here. So what's so special about having this arc length equal to 1? Well, what we can do is we can create our own scale for our angles. So as I mentioned before, the choice of the 360 degree is quite arbitrary, and I mentioned before as well I could choose a right angle here and I could call that 1 Ross, and I could call the 180 degrees there would become 2 Rosses. So I can choose my own scale. Now if I choose this particular scale here where this angle here is equal to 1, then that's really useful, because if we call this angle 1, then we know that the length of arc here is a value of 1 as well. So now we are able to equate angle directly to length. The angle is 1, the length is 1. We don't need to go through this scaling factor of pi upon 180 as we had to do with degrees. In this new scale that we've created, there's no need for the pi upon 180 because the angle of 1 relates directly to the length of 1. So we can relate angle directly with length without any scaling factor. Now this new scale we call the radians, and this value 1 is a value of 1 radian. So how many of these radians are in a full circle? That is a full revolution. Well, we know that, and it's quite simple because we know if we have a radius of 1, then the circumference of the circle must be 2 times pi times 1, so that must be 2 times pi, which is 6.28. So all the way around the circle is a distance of 6.28. We know that the distance from here to here is 1. So there must be 6.28 of these angles all the way around the circle. That is, a full circle must equal 2 pi radians. So finally, what's going to happen if we don't actually have a radius of 1? Because the radius could be any value. Well, that's quite simple, because we've seen when we looked at the circumference it's going to be 2 pi r. So everything's multiplied by r, and we said r in this instance is equal to 1, but r can be any value. So that means that if we were to look at the the length of an arc? Well, the length of an arc in radians is simply going to be the angle times the radius. So in this instance here, for example, if the angle here is just 1 radian, then we know that if the radius is 1, then this distance here round, which is the arc length, would be a value of 1. So if the radius was 2, then the arc length would just be 2 times this angle here in radians, which is 1, which is a value of 2. So by using radians, it means that we've got a direct relationship between the angle and the length. By using degrees, the relationship between the angle and length has an extra factor of pi upon 180. So now if I want to convert from radians to degrees or degrees to radians, we notice that we said that if the pi radians is equal to 180 degrees, then we can just use this in order to do the conversion. So for example, if we wanted to convert from degrees to radians, then we just get rid of the 180, so we divide through it by 180, we divide this side by 180, so degrees would equal pi divided by 180. So to change from degrees to radians, you multiply by pi and divide by 180. Alternatively, if you want to go from radians to degrees, then you could divide throughout by pi, in which case to get from radians to degrees, you multiply by 180 and divide by pi. So let's summarise everything we've learned mathematically. So we said that we can choose any angle that we want and we can call that angle 1. And every other angle is just relative to that angle 1 that we have chosen arbitrarily. But we've also seen that there's a useful way of choosing this angle of 1, and that leads to the measurement in radians. So we say that 1 radian is the angle subtended by an arc which is equal in length to the radius. So I'll say that again. 1 radian is the angle subtended by an arc which is equal in length to the radius. And we've seen that the reason for doing that was that it allowed us to relate this angle here directly to the length of the arc. So for example, if the radius was 1, then it would mean the length of this arc is 1, and we defined that as 1 radian. So it means that this angle here is the same as this length here. So if we had an angle of say 2 radians, then the arc length would be a value of 2. If we had an angle of 3 radians, then the arc length would be a value of 3. So that's always assuming that the radius is 1. But if the radius was, say for example, a value of 2, then all we need to do is multiply the angle here, theta, by the radius. So say for example, the angle was 1.5 radians and the radius was 2, then the arc length would simply be the 2 times 1.5, which would be a length of 3. So we can say then, more generally, if we call the arc length L and we call the angle theta and the radius r, then we can say L is equal to r theta. So this is a little equation that relates angle to length, and if its angle is thetas in radians, then all we need to do is multiply that angle by the radius, and that's going to give us our arc length. So we also noted that if the radius is 1, we know that the circumference is 6.28. So that means if this angle is equal to 1, there's going to be 6.28 of them in a full revolution, which is 360 degrees. So there's going to be 2.2 pi radians in 360 degrees. Or equivalently, we can say there's going to be pi radians in 180 degrees. So we can use this one here in order to create the conversion. So if we're going from degrees to radians, we simply take our degrees and we multiply them by pi and divide by 180. If we're going from radians to degrees, we simply take our radians and we multiply by 180 and divide by the pi. So let's say for example we have 360 degrees. So 360 degrees times pi divided by 180 is equal to 2 pi. So 360 degrees is 2 pi radians. So lastly, we should note that whenever we're doing any calculus with trigonometric functions, so they are circular functions, we're assuming that we're working in radians. Now, if we weren't working in radians, that would mean that the angles here wouldn't relate directly to the lengths of the circumference. They would be related via pi divided by 180. So we would have pi divided by 180 in every calculation. But if we are assuming we're working in radians, it means that the value of this arc length L and the angle theta are simply related by L equals r theta. So there's no pi divided by 180 in any of this. So that's why we always assume that whenever we're doing any calculations that we tend to work in radians.